All right. So, chemical reactions can be classified in many ways. Okay? The most basic is oxidation reduction. Oxidation reduction, which involves reactions with electron transfer and non-oxidation reduction. So we have the biggest category is it a, and we often call an oxidation reduction reaction a redox. Okay, redox, that's the way to say it. So you can either have a redox reaction or a non-redox reaction. All right, so today we're going to be looking at generally non-oxidation reduction reactions. Some of them technically are. All right, but also can classify as, so we're going to look at 5 different types of reactions. All right. So we have synthesis reactions. We have decomposition reactions. We have single replacement. We have double replacement. And we have combustion. I'm going to do a little key here. All right. So when I draw a stick figure man, that is a metal. All right. When I draw a stick figure woman, that is a non-metal. All right. And while the majority of my reactions here will be heterosexual, that doesn't mean that there aren't other things that can happen. It just happens that these reactions are going to look this way. All right? It's just a simplified version of way of thinking about this. So let's first look at synthesis reactions. All right? This is when 2 or more reactants form one product. Right? I like to put this in dating terms. Okay? So this is like when a man, all right, and a woman get together to make a couple. Okay? We often use the terms A plus B yields AB. Okay? We're going to look at a couple different types of synthesis reactions. All right? All of these, all right, are in your reference table. Okay? So binary metal oxide, non-metal oxide. There's a couple more here that are not in your reference table, but those probably will not end up on a state test, not that we're taking a state test in this. All right, so the most simple is the binary compound synthesis, and that is when we take an element and another element, okay, and we form a binary compound. And to form that binary compound, we have to find the charge on this and the charge on this and cross the charges. Iron, when in doubt, iron's going to take on a 2+ charge. So Fe 2+. Oxygen, if I look at my reference table, I'm going to see that oxygen is going to form a 2-. And then crisscross my charges. All right, I'm going to get FeO. And to balance this, I'm going to put a 2 in front. So that is binary compound synthesis. That one's nice and easy. Just find the charges of each one and crisscross them to find the product. Next up, we have metal carbonates. All right, this is where we have a metal oxide. And we have carbon dioxide. And we're going to make a metal carbonate. So what I'm going to do is take my metal, which is Ca. I'm going to find the charge on that. That is 2+. I'm going to cross that with carbonate, which is CO3 2-. So cross that. I'm going to get CaCO3. Okay. Metal chlorides are similar, except you're going to be taking a metal chloride, okay, and you're going to cross it with oxygen, and you're going to combine it with oxygen, all right, and you're going to get a metal chlorate, which is LiClO3, because chlorate is ClO3 1-, and lithium is 1+, and so you have a metal chlorate. This one is not in your reference table, so I wouldn't spend too much time on it. The big ones you're going to need are this, all right, metal, that, all right, and metal oxides, which we already did on the previous page, and then non-metal oxides we'll look at. All right. We have, and this is non-metal oxides right here, which is an acid synthesis. Okay? So base synthesis, we're taking a metal oxide, we're adding it to water, all right? And I'm going to get cross the metal Na 1+ with OH 1-, and I'm going to NaOH, and to balance it, I'm going to put a 2 in front, and so when I take a metal oxide and I put it in water, I get a base. And this is something that we covered the other day, okay, when we did our metal reactions. Acid synthesis, we take a non-metal oxide and we put it in water. This one is really easy to solve. So first you're going to count how many hydrogens you have on this side. I have 2 hydrogens on this side. And then oxygens always go last, so in between I'm going to have sulfur. I only have 1 sulfur. And then how many oxygens do I have on this side? I'll wait for somebody to tell me how many oxygens I have on this side. That's a 3 plus a 1. 4. There. Boom. Done. That's how you do that one. All right, and you end up here with an acid. Okay? So, I want you to predict the following reaction. Look up here, all right, at our examples and figure out what this most resembles. All right? So first, we have a metal oxide. And what is this? Carbon dioxide. So I'm going to look up at my examples here. Which one involves carbon dioxide? That would be a metal carbonate. So I'm going to find my charge on my metal, and I'm going to cross it with the charge on carbonate. So what is my charge for magnesium? Magnesium is pretty highly reactive, not as much as the with this row. So magnesium is right here. It's going to have a 2+ charge, right? So we're going to cross it with carbonate, all right? CO3 2-. Crisscross applesauce, hands in your lap. There's 2 and 2, so I'm going to reduce that down to 1 and 1. So it's going to be MgCO3 as my answer. It's going to make a magnesium carbonate. So I have a metal oxide, all right, and carbon dioxide, and I get a metal carbonate. Okay? All right, and there's actually no balancing I need to do here. All right, that's all our examples of synthesis. Let's look at a decomposition reaction. All right, this is where yeah? Synthesis means you're taking 2 or more reactants to make one product. Now, there may be a byproduct for making TNT. Now, you would still call it synthesis because you're pulling out a specific thing, but it may be like a double replacement reaction. So, let me go through all the reactions and you'll see what I mean, okay? All right. This is where the reactants break down into 2 or more products. All right. So this I'm going to take, I have a little man and a woman. Okay. And they are going to break up. This is a breaking up. We often write this as AB yields A plus B. This is essentially the reverse of a synthesis reaction. So, on our first page, we produced FeO. All right, here we're going to get 2Fe plus O2. Now, remember, it's not just oxygen because oxygen can't exist by itself. All right, oxygen, okay, is highly reactive. Okay. All right, metal carbonates are going to make a metal oxide, which is CaO plus CO2. Oh, and I forgot to write something. So this is a binary compound. All right, and then we break down into an element and an element. All right, here we have a metal carbonate breaking down into a metal oxide and carbon dioxide. Okay. And then a metal chlorate, just a reaction of a metal chlorate synthesis. All right, I'm going to get LiCl, 2 of those, all right, plus O2. I'm going to get 3 of those. So here I have a metal chlorate. This is metal chloride and oxygen. All right, I want to make a note. All reactions here are theoretical. Many require extreme conditions to take place. So many of these reactions, though it looks like, oh, I just mixed this and I mixed this and I'm going to get this, that's not actually really what happens. Many times it takes high heat, high pressure, really crazy stuff in order for these reactions to happen. All right? So these are all theoretical. All right? And our base decomposition will result in a metal oxide, NaO, plus H2O. All right? No, Na2O. Ooh. And this is going to result in SO3 and H2O. So this is base, metal oxide, water, acid, all right. All right, so we're going to predict the following reactions. We'll do this first one together. So I have HNO2, that is an acid. I know when I get an acid, I'm going to get a non-metal oxide and water. First, I'm going to write down water. Okay? So here I have actually H2N2O4. All right, if I take H2 out and I take 1, all right, I'm going to get N2O3 is what's going to be left, I believe. Okay? Because if I add this all up, that's going to equal this. Okay? So this is an acid, this is water, and this is a non-metal oxide. All right? I essentially subtract the water out of the total number that I have here, okay? All right. Here, all right, I'm going to look up at the top. I don't have a base, so it's not that one. I don't have a chlorate, so it's not that one. I don't have a carbonate, so it's not that one. So this must be a binary compound decomposition. right? So this is going to break apart into mercury metal and oxygen. And I know oxygen has to be, all right, O2. So I'm going to have O2, all right, plus mercury metal can just exist by itself. I'm going to have 4 mercury metals in order to balance it out. All right? So we have a binary compound going to an element and an element. All right? Single replacement reactions. I guess you could call this like cheating reactions, okay? All right. And this is where an element reacts, all right, with a compound, all right, to replace, right, the in the compound. All right? So I can draw this 2 ways. And I'm going to have man with pants on. Not that women can't wear pants, but he's got breeches on. All right? This could go to be so she left this man to go to this man. Now I could write it the other way around too. She's just going to be wearing a skirt. I guess she's not doesn't have a top on. Of course, he's leaving her for the woman without a top on. All right. So here we've replaced it with another metal. Here we've replaced it with another non-metal. But those are both single replacement reactions. So here in a metal replacement reaction, the copper is going to come in and replace the silver. So the silver is going to come out. Okay. And then I have to find the charge on copper, which is usually 2. Copper 2 plus. And nitrate is NO3 1 minus. I'm going to cross those. I'm going to get, all right. So I have here a metal, all right, and an ionic compound, all right. This is the metal that got kicked out. All right. And this is the ionic compound with replaced metal. Crazy, crazy. And if I need to slow down, please tell me. So in a non-metal replacement, now the non-metal is going to come replace the non-metal. So here we have a non-metal. Okay, and here is an ionic compound. Okay. All right. So the chlorine is coming and it's going to replace that. So I'm going to get actually NaCl, and I'm not even crossing it because I'm just so familiar with that. All right, but you would do the same thing, find the charge on Na, the charge on Cl, and then I'm going to end up with I2. Iodine's another one of those ones that can't be by itself. All right, so this is ionic compound with new non-metal. All right, and this is non-metal that was kicked to the curb. Caveat of this is the metal will only replace this metal if it is more reactive, and the non-metal will only replace this non-metal if it is more reactive, and that's where we use the activity series. Okay, if this was not more active than iodine, then we would put no reaction here. All right, double replacement. I'm just going to do this one in pictures because that's the best way. So we have a man and a woman, and then we got the man with breeches and the woman wearing a skirt, who's got a really long arms. All right, they're going to switch partners. Okay, this is a swingers reaction. Okay, so this man is now going to be with the woman wearing the skirt, okay, and the man in the breeches is now going to be with the woman in the triangle dress. See, they switched partners. Right? So in this, the silver is going to get with the chlorine, and the sodium is going to get with the nitrate. All right? This is the sort of reaction where I'll have to look at and see what's soluble and what isn't soluble. Okay? So I know Ag is going to take on a 1 plus charge, and Cl takes on a 1 minus, so I'm going to end up with AgCl. And this is actually a solid. Okay, I figured that out with my solubility rules. Okay, and then I have Na 1 plus and NO3 1 minus, so I'm going to get NaNO3. Right, so I have an ionic compound and another ionic compound, and then ionic compound with switched ions. And this is also another ionic compound with switched ions. All right? Making heroin you have to have opium. I mean, not necessarily. They do use chemistry. Many of them probably don't understand the chemistry of what they're doing. If they did, their products would be better. All right, if you've seen Breaking Bad, part of the thing that makes him famous is the quality of his product is so good. So most of them are just looking up the recipes online like they would look up a recipe for anything else, and they're cooking it up. But if they understood the actual chemistry behind it and the mathematics and all of that, they would make a better product. But yes, in essence, they're practicing chemists. It's not just mixing it. A lot of these require specific situations and practices. So like you could push the reaction further to completion by heating it up, or they would understand how to purify their compound. They also wouldn't probably use as nasty of containers as they use. They would use high quality glassware. There would be quality control, a lot of those things. That's why you always choose, their yield would be a lot better is what it would be. Their yield and the quality of their product would be better, because whenever they create a product, there are some impurities based on that have to do with how they went through the process of doing their reaction. The better your practices are, the less impurities, the higher quality product you have. Well, Kool-Aid is not a chemical reaction. Making Kool-Aid is not a chemical reaction. That's just dissolving something in water. And Kool-Aid is just a mixture itself. It's a mixture of sugar, citric acid, ascorbic acid, and a flavoring, and then usually a coloring. So those are just mixed together in the granules and ground up. So it's just dissolving something. That's a physical change, not a chemical change. Yes, because with Kool-Aid, I dissolve it. If I just let it sit over time, the water would evaporate out, and then I'd be left with the Kool-Aid powder at the bottom. Or I could boil the water off. Yes. All right. All right, double replacement reactions. I'm going to have to tag this video on YouTube as not appropriate for children. Also result in a further decomp reaction. So you'll make one of your products will further decompose. So for example, NH4OH will decompose to NH3 and H2O. H2CO3 will decompose to CO2 and H2O. And H2SO3 will become SO2 and H2O. All right. So let's do a couple of reactions. We're going to cross, so calcium is going to combine with chlorine, and hydrogen is going to combine with CO3. Okay, and there's two hydrogens. All right, so Ca, calcium has a 2+ charge, chlorine has a 1-, so I'm going to get CaCl2, and now I'm going to add it up. 2 H's, H2, and then 1 carbon and 3 oxygens. Alright, Or you could have, the other way you could do it would be H is 1 plus and CO3 is 2 minus. If you cross them, it's H2CO3. So there's two ways to go about this. Because this one was already balanced on this side, I was able to just add things up. Normally you would have to find the charges and cross them. But we're ending up with H2CO3, which we just learned will further decompose to CO2 and H2O. So I'm actually going to end up with CaCl2 plus CO2 plus H2O, which is actually one of the reactions. Is this one of the, I don't do this actual reaction because I don't use hydrochloric acid, but I add citric acid, which will do the same thing. You will see it bubble. So, because CaCO3, calcium carbonate, is just chalk. All right. So here I came up with one of my products that's further going to decompose, so I had to write it a second time. All right, one more left, and this one's fun. Combustion reactions. This is burning stuff. Usually in the presence of O2. All right, they happen quickly. All right, they produce heat. And usually produce light and fire. So you're like, I know this reaction very, very well. I know some of you have probably played around with this reaction probably a little too much. All right. When the reactant being burned contains carbon, hydrogen, and oxygen, products are CO2 and H2O. Sometimes CO, carbon monoxide, if combustion is incomplete. All right. If reactant contains sulfur, okay, all right, products will also contain SO2 and sometimes SO3. Okay? If contains nitrogen, you're going to get N2 or and NO or NO2. Right? Mainly you're going to be looking at where your products are CO2 and H2O. Okay? So here I have glucose. I'm burning it in oxygen and I'm going to produce CO2 and H2O. Okay? And we'll balance this. Here, this is an amine, I think. I'm burning it in oxygen. I'm going to get CO2, H2O, and into nitrogen gas. All right, some hints. right? Often easiest to balance carbons first, then balance hydrogen, then balance oxygen. All right. So I'm going to balance these two up here for you. All right. And then I'm going to let you balance these three, and then we'll check them. All right. C6H12O6 plus O2. So it says balance carbons first. So I have 6 carbons here. So I'm going to put a 6 here. Now my carbons are balanced. I have 12 hydrogens here. I have 2 over here, so I'm going to put a 6 in front because 6 times 2 is 12. All right? Now I'm going to count how many oxygens. I have 12 oxygens here, plus 6. I have 18 here. All right? And there's 6 and 2. There's only 8 here. I don't want to put a number in front of this because that will change my carbons and hydrogens. So I'm going to assume I'm always going to have 6 oxygens from here. All right? So I need 12 oxygens. I have 2. 2 times 6 is going to give me 12. Now I'm balanced. All right? Sometimes writing these out on a separate sheet of paper is helpful in doing the counting. All right, here. 2 carbons. I'm going to put 2 here. 2 hydrogens. That's good. I have 2 nitrogens. That's good. All right, I have 6 oxygens here. And I have 4. All right. All right. 5. I know I'm not going to be able to balance that. All right. And that this 2 is not going to work out. So I'm going to stick a 2 in front here now. All right. Now I'm going to rebalance this. I'm going to get rid of this and make this a 4. All right. 2 times 2. So I'm going to put a 2 here. And a 2 here. Now I'm going to recount my oxygens. So sometimes I have to go back and redo this. I have 8 plus 2 is 10. All right. 8 plus 2 is 10. Here I have 2 times 4 is 8. 8 plus 2 is 10. I'm balanced. All right. So down here you have 3. All right. I want you to take a few minutes and balance these 3. Remember, do carbon first, then hydrogen, and then oxygen. I'm going to also give you a hint. Usually when the carbon is odd, you're going to want to put a 2 in front here, but not always true. I'll let you play around with it. I'm going to take this off the screen and do it by myself, okay? And then I'll bring it over and we can go over them. So take a second to solve those. All right. Whenever you're ready, you can check your work on the screen.